partial fraction decomposition. You just split up this integral into two different fractions with this strategy of having variables on top of those two different fractions. You solve for those variables in an equation that we turn that into, and then you plug that back into the integral. That is what all you do with these problems. So just let me write it out. The strategy is you're going to have variables on top that you can pick. You literally don't have to put a, but it's a lot easier to do that. And you split up the denominator. So all these are always going to go something like this. You're going to have a over denominator 1, b over denominator 2. If we had another equation or another relation of x in this denominator, then we'd have another one. The only little thing with that is that if this was a quadratic and it was like x squared, then on the top you're just going to do ax plus b on the top, and then this next part would just have to be c. If this was also a quadratic, then you'd have to have cx plus d, and then this part would have to be e. This is also a quadratic. If it's not, leave it e, but so on and so forth. Obviously, the more that's in the denominator, the little bit more trickier that the problem's going to be to solve. But they really don't get too crazy, too bad. This one, we're going to split up like we were just talking about, and then just check out those exponents. We want to look at the exponents in the denominator. X to the power 1, x to the power 1. So we know we're just going to have a, and we know we're just going to have b. Boom. That's the main trick. Once you get the hang of that, you can solve these problems. So we have this now, and we just need to turn this into an equation so that we can solve for a and b, and then plug it into an integral and integrate that and get the answer. So to turn that into an equation, what you just want to do is multiply this that we found by the original denominator. Okay? And so what that looks like is apply it to each term. So 2x plus 1 times x minus 1 multiplied by this. Well, let's throw it in the numerator. What cancels? The 2x plus 1, right? So then it's just a times x minus 1. 2x plus 1 times x minus 1 multiplied by this. Throw it in the numerator. What cancels? The x minus 1 and the x minus 1. So it's just b times 2x plus 1. Okay? We're just multiplying the original denominator to each term in this new function that we have made up, pretty much. And so that little trick there is that now that we have that equation, you always just set it equal to the numerator in your original integral. And that is always going to be the case. This is always how you're going to go about it. This is partial fraction decomp strategy. This is what you do. And so now that we have this equation, we just solve for, we want to plug in values for x that's going to help us solve for a and b. And what that means is, what values for x can I plug in that's going to cancel out a variable so that I can solve for the other variable, right? Well, let's look. Right here, if I plugged in what for x would give me 0, that would multiply to a, because anything times 0 is 0, so that way a goes away, and then I can plug in that same value for x here because it's x, and then I can solve for b. Well, if I plugged in 1 here, right, that'd be perfect, because this would go to 0, and then this would become not 0, so I can solve for b, right? So let's try it out. So x equals 1, a times 1 minus 1 plus b times 2 times 1 plus 1 equals 5 times 1 plus 1. This is when x equals 1. This is our equation when x equals 1. Well, a times 0 is 0. plus 3 times b is equal to 6, right? And then this is when it's just simple algebra. So 6 divided by 3, b equals 2. All right, so we found b. So what we can do is, if we really wanted to, we can plug b back in and then plug in some simple value for x and solve for a. And I think that's what we're going to do. We don't want to plug in 1 again because then a is going to go away and we're not going to be able to solve for it, right? So let's just plug in something pretty simple here, like 2. Or 0 would be even better. So if we do 0, we have a times -1, 0 minus 1, plus b, which is 2 now, times 2 times 0 plus 1 equals 5 times 0 plus 1. Right? That's when x equals 0. So now we have -a, plus 2 times 1, 2 times 0 plus 1, so 2 times 1, which is just 2. 0 plus 1 is 1, and then -a plus 2 equals 1, so minus 2, 1 minus 2 is -1. So -a equals -1, divided by negative, and we get a equals 1. So b equals 2 and a equals 1. All right? Cool. Pretty cool. This is the step-by-step process that you do in every single partial fraction decomposition problem. Now what we just have to do is plug in our values that we got for this original equation that we set up initially into an integral, integrate that, and then we get the answer for this, essentially. Pretty cool stuff. 1 and 0 it's just what made sense to do. You can literally plug in any value you want into x, and you'll end up getting there. However, you do need to just understand that the idea is to plug in values for x that's going to end up canceling one variable or the other, so that we can actually end up getting somewhere. Also, you can definitely set up a system of equations. If you wanted to plug in any random 2 values in for x, get 2 different equations relating a and b, you could set up a system of equations. We will do a problem like that. This is a little bit more simple if you can cancel them out. But yeah, we have values for a and b now. So what that's going to look like is we take this, and we plug it into there. Oh, it's like Christmas colors. Integral of 1 over 2x plus 1 plus b, which is equal to 2, over x minus 1. So we're just taking this original thing that we literally made it up in the beginning, and then what we were doing was just solving for a and b for that, and then we plug that back into the integral. That is what we do. All right, in respect to x. So to solve this, let's just split it up into 2 different integrals, because we're allowed to. I'm pulling that 2 out front because it's being it's in the numerator and it's being multiplied by 1. And so, oh shoot, don't forget your dx. If you can't see this, that's okay. I'm literally going to show you exactly what it is. But a lot of these problems are going to end up giving you natural log and natural log. This is just natural log of 2x plus 1 plus 2 natural log of x minus 1. If you can't see that, don't worry, I'm going to show you right now. It's a u sub. So you always just want to u sub the denominator in this kind of scenario. What's the derivative of 2x? It's going to be just 2, right? And then 1 is going to go away, so it's going to be 2 dx. And then we need to get dx on its own. so that we can actually substitute it. So now if we sub that back in using the u substitution method, this becomes 1, this is equal to u, dx is equal to half du. So this would be half times du, and then since half's being multiplied, we can pull it out in front of the integral. Okay? So I misspoke earlier, so my apologies. It's not just the natural log of 2x plus 1, it is 1/2 natural log of 2x plus 1. And that's why it actually helps to write out the u sub. I think I would have caught myself while writing it, but yeah, if you have like a coefficient in front of this, it's going to be a hint that you're going to have something in front of your natural log. Writing out the u substitution's a good idea. This one obviously has a 2 in front of the integral, so it's going to just be, there's going to be a 2 there anyways, but that doesn't really have to do with the u substitution. It just has to do with the fact that the 2 is in the... So let's just write it out. What's the derivative of x minus 1? It's going to be 1, right? 1 dx. Let's write out the u sub. Don't forget the 2. 1 over, what's x minus 1 equal to? It's going to be the u. That's what we're substituting. Dx is equal to du. All right? And then what's the antiderivative? What is the antiderivative of 1 over x? Hopefully you can remember that it is natural log of x. That is kind of just something you remember. That is because the derivative of natural log of x is 1 over x. So the antiderivative of 1 over x is natural log of x. That is what an integral is. And now we can write 1/2 natural log of u, which is 2x plus 1, plus 2 natural log of u, which is x minus 1. Right? And then what do we not want to forget? The plus c. This is partial fraction decomp. All right? It's building off a little bit of like very, very, very beginning Calc 2 and end of Calc 1 stuff where you just needed to be able to do your u substitution with integrals. But the initial setups are always going to be pretty similar. So that's the step-by-step process in all these problems. Let's step it up a notch and try a little bit of a harder one.